Hi, my name is Turan Erdogan, and I'm the CTO and a co-founder of Semrock. And at Semrock, we manufacture high-performance optical filters that are used in a variety of different applications. And today I want to talk to you about a very, very special product that we just came out with this year. Before I do that, I want to start by asking you a question. Did you know that you can tune an optical filter, thin film optical filter, over 60 or even 80 nanometers across the visible wavelength range? And did you know that you can do this while maintaining all the great properties of thin film filters, like high transmission, very steep spectral edges, wide out-of-band blocking, and, perhaps most importantly, the ability to transmit an image through the filter while you're measuring the spectrum? Now, you may or may not believe what I just told you, so let me actually show you. We have a demonstration here, and all this is a white light-emitting diode that's collimated and being transmitted through one of our new Versachrome tunable optical thin film filters. And that filter is being rotated from 0 to 60 degrees and back again. Here I have a beam splitter that's picking off a little bit of the light so I can measure the spectrum and show it to you in real time, and then the beam is transmitted onto the screen back here. Now up here, we're actually showing the spectrum that's being measured of this bandpass filter. And the filter is actually designed to transmit light between wavelengths of about 620 nanometers when it's at normal incidence, all the way down to about 550 nanometers when it's at 60 degrees. So that's a 70 nanometer tuning range for this particular filter, all while transmitting a potentially two-dimensional imaging beam of light through the filter. So why do tunable filters matter? Why should anybody care about having a good tunable filter, especially one that can transmit an imaging beam? Well, take, first of all, biological imaging applications like fluorescence imaging. With a tunable thin film filter, you can do things like optimize the signal-to-noise ratio in a fluorescence imaging system, especially for very low concentration imaging, very low concentration samples. You can also, for example, do ratiometric imaging very precisely, even when the fluorophores have only very minor changes due to environmental conditions. You could multiplex very densely spaced fluorophores. You can get rid of autofluorescence background, and you can even make more accurate measurements of tissue samples in pathology applications. In addition, if you look at some broader applications outside of biology, hyperspectral imaging is a very important technique that's growing in popularity in a number of areas. Consider some broader applications, such as those that use hyperspectral imaging, which is really growing in popularity. With a tunable filter like this, you could make better, faster, cheaper instruments for applications like remote sensing, medical imaging, agricultural analysis, manufacturing, where you could do, for example, online process monitoring or quality control, or even forensics, where you could make portable instruments that would allow you to detect the cause of death at a crime scene. Now, you might be saying to yourself, filters have been around for a long time, so what's so new about this technology? Well, thin film filters are regarded by many people as really the ideal spectral filtering technique for especially optical imaging systems because of their high transmission, very steep spectral edges, and wide out-of-band blocking. However, filters have long been regarded as a truly fixed filtering mechanism. That is, if you want to change the spectral characteristics, you have to have multiple filters, and you have to swap them somehow using, for example, a filter wheel. Now, on the other hand, diffraction gratings are a great component for scanning wavelength. That is, if you have a scanning measurement system and you want to be able to tune over a wide range of wavelengths, a diffraction grating is almost an ideal component to do that. The problem is, diffraction gratings aren't perfect either. They have a number of limitations. First of all, the spectral performance of diffraction gratings is not nearly as good as a thin film filter. They have, for example, limited blocking out of band, the edges aren't so steep, and perhaps more importantly, because diffraction gratings have to map wavelength onto angle, you can't transmit a two-dimensional image through a diffraction grating. Semrock's new Versachrome tunable thin film optical filter technology is something truly unique, and we're very excited about implementing it in a wide range of applications. If you have any questions at all, or any ideas you'd like to share with us, we would love to talk to you. Just visit our website at www.semrock.com and contact us by phone or email at any time.